everyone, my name is Wenxing Ding, and I am presenting the paper Calibration with Privacy in Peer Review. This paper is joint work with Gautam Kamath, Weina Wang, and Nihar Shah. It is well known that scores provided by people are frequently miscalibrated. In the application of peer review, reviewers may be strict, lenient, extreme, moderate, etc. This leads to unfairness in peer review. A number of algorithms have previously been proposed to calibrate reviews. However, the outcomes of applying those calibration algorithms are found unsatisfactory. We identify a key challenge in addressing miscalibration. The calibration algorithms may leak information about which reviewer reviewed which paper. Towards this challenge, we assume an open review model in this paper, where all submitted papers and all reviewers are available publicly. However, the information about who reviews which paper is not. Now let's look at a simple example that illustrates why applying calibration algorithm can leak information. Consider two reviewers, one being strict and the other being lenient. They are both potential reviewers for a paper, which receives lukewarm review. Upon receiving the review of the paper, the conference decides to use calibration and then decide to accept the paper. Then the adversary, who wants to guess the reviewer of the paper, has necessary information to make the guess that the strict reviewer is the reviewer of the paper. Therefore, our goal is to design methods for the conference to accept better papers while guarding against privacy leakage. Now let's look at the problem formulation. We consider a simple yet challenging model consists of two reviewers and two papers. Each reviewer has a miscalibration function and some distribution of noise. Each paper has some true quality. We consider the miscalibration function, the distribution of the noise, and the distribution of the quality are known to both the conference and the adversary. The score of the paper is a combination of the reviewer's miscalibration function and its noise. We use F to denote the marginal PDF of the scores given by a reviewer. In the two-paper, two-reviewer setting, there are two possible assignments. We denote it as A1 and A2. The goal of the conference is to accept the paper with higher true quality, and it uses MAP if it wants to calibrate without privacy. And the error of the conference is the probability that the conference accepts the lower quality paper. For the adversary, its goal is to guess the assignment. It predicts the assignment via a maximum a posteriori estimation. Error of the adversary is the probability that the adversary guesses the assignment wrong. We also establish Pareto frontier, which is a set of all points of the conference error versus the adversary's error trade-off, such that the adversary's error cannot further increase without increasing the conference's error. And the calibration strategy is said to be Pareto optimal if for any given threshold of the conference's error, it maximizes the adversary's error while ensuring that the conference error does not exceed the given threshold. We consider two settings, one being noiseless, where the noise of the reviewers are all zero, and one noisy setting. We also look at two types of errors, the per instance error, which is an error under given score, and there's an average case error across the distribution of all scores. Now let me introduce our main results. We established the Pareto frontier of the trade-off between the privacy and utility, and we design explicit computationally efficient algorithms that we prove are Pareto optimal. First, let's look at the noiseless setting under the per instance error. In the noiseless setting, because the reviewers have noise 0, given the scores, the conference can compute the exact true quality of the paper using the inverse function of the reviewer's miscalibration function beta. Therefore, the Pareto frontier in the noiseless setting for the per instance error is shown as in the plot. Now first, let's look at what happens at the point x. At this point, error of the conference is 0, and the adversary can only guess the assignment based on the scores. In this case, one paper has higher estimated quality under both assignments. And therefore, in a calibration algorithm, we say that if one paper has higher quality under both assignments, we will accept the paper. Now let's look at what happens at the line segment. The line segment has slope 1, and it starts from the origin, and it ends at the point where the error of the adversary equals the error of the conference, where the error of the adversary is the error that the adversary guesses the assignment based on the scores only. In the algorithm, the conference does calibration under the true assignment with some probability p, and does calibration assuming the wrong assignment with probability 1 minus p. In this case, we make the error of the conference and error of the adversary to land on this line segment of the Pareto frontier. Note that in this case, when you calibrate under the true assignment or calibrating assuming the wrong assignment will give you the acceptance of different papers. In our theorem, we prove that the per instance calibration algorithm is Pareto optimal. Now let's look at the noiseless setting under the average case error. In the algorithm for the average case error, we make use of the per instance algorithm with the error of the conference being 1. The error of the conference being 1, meaning that we are at the endpoint of the line segment. Now let's look at the average case algorithm, which makes use of the per instance algorithm with the per instance error of the conference being 1. Note that when the per instance error of the conference is given to be maximum at 1, then the per instance algorithm will choose some probability such that the error of the conference and the error of the adversary will land at the endpoint of the Pareto frontier. We use C to denote the error of the conference for running the per instance algorithm with error of the conference being 1 for all scores. And if the given maximum allowable average case error of the conference is greater than C, then we will simply run the per instance algorithm for the error of the conference being 1 at every scores. Otherwise, we will toss a coin and we either run the per instance algorithm or we calibrate under the true assignment where the conference has 0 error. We proved that the average case error algorithm is Pareto optimal. Now let's look at the noisy setting under the per instance error. In this noisy setting, the error of each reviewer has Gaussian distribution. The conference can no longer compute the exact quality of the paper, but it can compute the probability that one paper has higher quality under each assignment. Then the Pareto frontier in the noisy case is shown as in the plot. It's very similar as to the noiseless case. It contains a point when one paper has higher quality under both assignments, and the algorithm does the same, that it accepts the paper. Otherwise, the Pareto frontier is a line segment. However, this line segment no longer starts at the origin and does not have slope 1. Note that in this case, error of the conference always exceeds 0 due to the noise in the reviewer's review. And when we land at the line segment, the conference again chooses some probability p and calibrate under the true assignment with probability p and calibrate assuming the wrong assignment with probability 1 minus p. In summary, we first identify the problem of privacy in calibration, and then we initiate a theoretical study with the formulation problem that incorporates various key challenges of the more general setting. We provide explicit computationally efficient algorithms for calibration with privacy that optimally trades off the error of the conference and the error of the adversary. And we establish the structure of the Pareto optimal curve. And we observe that, interestingly, there is a linear trade-off between the two errors up to a certain point, after which error of the adversary does not increase anymore, even if the conference adds more randomness in its protocols. Thank you.